Thank you, Steve, for having me. It's a real honor, really, to be here and to actually give, to say whatever I want for 1 hour and, not too many questions asked, at least, not yet. So, okay, so I just want to just give you some background about how my journey with Temporal started. So during my master's, I had to create a system which would automatically classify classical music based on the period of composition, like which was it from the Gregorian era, was it Renaissance, Baroque, So I had that problem at hand, and I was just playing around with some features and pattern classification and all, and then finally the only thing that worked were these features called Mel frequency capsule coefficients. So I didn't give it much of a thought. I said, okay, it worked, that's it, I'm done with my master's, I'm out of here. But then I realized that these Mel frequency capsule coefficients, or MFCCs as we call them, are very crucial in representing timbre. At least in the music information retrieval domain, this computational signal processing, acoustic domain, that these MFCCs have been used for several tasks, such as classification of mood, genre, emotion, identity of the singer, so many things. And then I realized, why are these MFCCs so good? What is it about timbre? So my thinking about timbre sort of stemmed from there. And then another thing I realized is that when I went on to do my PhD, I was just curious, like, okay, when I listen to music, I never pay attention to the lyrics. For me, it's just about the way it sounds. I don't even know the lyrics of my favorite songs. I have no idea. Honestly, I don't know. But I know the lyrics to the songs of my daughter's nursery, these rhymes and all, unfortunately. But I just don't know. But I just love the way it sounds. And even if my favorite piece of music is played on a speaker versus some crappy, like your crappy speaker versus some beautiful, high-end Bose speakers, I'm sure that I would enjoy the one with the Bose speakers more. It's just, I need to hear all the sounds. I need everything, right, to feel that. So that's when I thought, okay, so I just wanted to know why I like what I like. That was the question. But then I realized I had to take a step back and say, what am I hearing? What is it that I'm perceiving, right, that enables me to like what I like, or leads to some sort of aesthetic or emotional response? So that for me, for lack of a better word, I ended up calling it timbre. Again, like, okay, it's just the way it sounds. Let's call it timbre and let's see what's happening in the brain. But, and that's how it all started, the journey, and I think the presentation will take you through that journey. But then another thing on the side, as I was growing up, I had this cousin who passed away when she was very young because she had some form of cerebral palsy, and she had a lot of cerebral atrophy. And the thing is that she would not recognize her own mother, or, her cognitive skills were almost non-existent. Motor skills, cognitive skills, she's probably, she's, if you were to compare her with a day-old infant, maybe that infant would have better cognitive abilities, whatever they have at that age. But the interesting thing was, when she would listen to some sounds or certain kinds of music which sounded bright, sort of tinkling sort of a thing, then she would calm down. And then that's really fascinating for me, thinking that, okay, this is a brain which has not developed much, yet it does respond to some quality of the sounds. So for me, I found that amazing, like, oh, she's responding to probably the timbral qualities. I didn't know that back then, because I was quite young. I didn't know what timbre was. I don't know what timbre is still now. I don't know. But the thing is that when I think about it now, it made, it all the more gives me some evidence that timbre is such an essential quality, such an important, vital quality of sound and music, and it is so unfortunately understudied. So when I started putting this presentation together, I just thought, okay, I need a picture for timbre. And I typed in timbre on Google, and then this popped up. It's actually called Timbre, and it's an artist who created this, and it's called timbre. And I thought, yeah, that's pretty much timbre. It's something, it's abstract. You see some patterns, I see something, okay. And then when I have to put together this multidimensional, concept of timbre with a complex system such as the brain, so that really is extremely, it has its own challenges, of course, but to put a multidimensional thing and a complex system together is quite tricky. So in order to first understand where or how timbre is processed in the brain, we need to first take a step back and say, okay, how am I defining timbre, or what am I investigating, so that then I know, then I can find out where it's processed in the brain, and then how will I go about interpreting it. So all the content that I'm going to be presenting, I decided to divide it into these 4 modules, right? So timbre processing in the brain can be discussed in terms of the viewpoint related to levels of abstraction of timbre, and then the temporal span, which is related to, when do we start forming this perceptual concepts of, like this perceptual concept of timbre? Is it within a few milliseconds, a second, 2 seconds? How do we create this percept of timbre? And then talking about the paradigms, how do we investigate the brain? How do we investigate timbre in a setting where it's more realistic or more naturalistic, right? And then moving on to modeling, which is more related to what the neuroscience field is going to do in the future and what they're doing now already, right? So let's just get into each point. So let's start with viewpoint, levels of abstraction. Okay, so till recently, I would say most of the work that has been performed in neuroscience related to timbre has been based on levels of abstraction of timbre. So let's see what that means. So levels of abstraction, they kind of serve as basis to hypothesize where timbre is encoded in the brain or what to expect, right? So what do I mean by that? So low to mid levels are associated with the representation of acoustic structure in the brain, right? So you can say that I can synthesize a very careful, I can carefully synthesize a timbre, right? And then do some systematic manipulation and see how perceptually whether we can identify that, and then see where such changes are processed in the brain. And at higher levels, it's associated with sound source recognition and categorization. So let me just go a bit into details. So like I said, one could synthesize certain timbres and carefully check where certain slight manipulations are processed. Or you can also have other descriptive summaries such as brightness, roughness. These are more perceptual descriptive summaries, which then they form these basic dimensions of auditory sensation, right? Which then aid to categorization or recognition. So this is like a mid-level property. So you can do that, and this typically has been a very common choice for psychophysical timbre experiments, right? To give different instrument sounds to get this mental representation of how similar or dissimilar they are and all. So you can take those and then look at where they're processed in the brain or how they're represented or encoded, and then try to figure out, okay, what is it actually? What's the brain capturing? Is it capturing the acoustic properties, or is it capturing the differentiation? So what is actually happening? So from all these, there's certain things that people have at least there's been some consensus on certain things. So, and I'll come to that in just a second. So the higher level, representations of timbre in the brain are related to brain responses to categorical distinctions of sounds, right? So it could be related to musical instruments or speaker or gender or human action sounds. So it's just to say that if I'm going to have the same person speaking at the same pitch and loudness, two different speakers, same pitch and loudness, so what is it that's distinguishing both of them? So timbre, that it acts as a vehicle for categorical distinction. So that's another way of how people have looked at timbre in the brain. So what have they found so far, right? Until recently, at least. So, well, there are dual pathways in the brain which represent the where and what of the sound. Now, the posterior dorsolateral stream encompasses both spatial and language functions. It's the one you see in red. So stemming from the auditory cortices, the primary auditory cortices, which is like the place where the sounds from the brainstem go to. And then from there, they go posterior dorsal, and they kind of converge in the frontal areas. But that's related to spatial and language functions, and that's why they call it the where pathway. And then the antroventral auditory pathway, which stems from the primary auditory cortex, comes a bit lateral and anterior, and again converges more in the frontal regions. And that's important in auditory pattern recognition and object identification. And that is hierarchically organized. Since we're talking about timbre, it's typically associated with what, Not necessarily where, but of course, timbre can also contain information about where something is. For example, I have two violins playing the same note, and if I close my eyes and based on the loudness or the properties of, maybe the echo that the room catches upon on, that also gives me some idea of spatial, location or direction. But typically, so far, that has not been as much studied. It's more related to what is the sound. So, so this what pathway in the brain, right? The idea of hierarchically being organized, what does that even mean? So, starting with the primary core area, which is the primary auditory cortex. So think about it as where sound is sort of analyzed spectrally, right? Temporally spectrally, but it's more like a frequency decomposition. And then you have, what you see is that as you go from the primary areas to the secondary areas and to the frontal areas, you're going up the levels of abstraction. So in one sense, you can say that, yes, when we hear a sound, our brain automatically does some sort of frequency decomposition, but then it has to put these things together, right, in order to create this concept of timbre that we can actually say we consciously perceive as well. So at least so far what they have said that there is that sort of, as you go further away in terms of the pathway from the primary areas to the secondary to the frontal areas, you're going up levels of abstraction. Okay, now, so when I was reading this literature before I did my first neuroimaging study, I kind of realized that, okay, most of the studies that have been done on isolated sounds, so whether it's carefully synthesized or it's sounds of instruments, but they're always presented in isolation. And now the thing is that how does the brain actually, how do these results fare in the context of music? And when we listen to music, so many tones at the same time, so many instruments are playing at the same time, so much is going on. How can I translate those results into, music? And what does timbre mean in music? How do we define timbre in music? Maybe you can let me know, but I tried. So that was a question that I posed, and I began to wonder, okay, is timbre, because I say I just like the way it sounds. So what does that mean? What is it actually representing? Is it representing some sort of, yesterday there was a talk on guitar, the metaphors and how with the amps and how the guitar sounds are and what they like. So is that how we define timbre in music? Like, okay, it sounds full, it sounds rich, it sounds mellow, it sounds pleasant, it sounds nice. Is it that? Or is it related to, just the overall emerging sound of a particular band or an artist? For example, Pink Floyd is his own genre in a way. Like he has this, it's not one person, but, they have their own specific genre or sound or timbral environment that they create. Same way with some other bands, they have very specific. Sometimes you can just identify the bands based on the way they use the instrument. So some sort of an overall emerging property that kind of gives you the idea, okay, this, it sounds like this band or this person. Or is timbre in music only related to the genre? Okay, this is hip hop. It's hip hop. All you need is a second to even identify, yeah, that's hip hop or that's rap or that's classical or, and we don't even need the temporal information. We can identify that. So is timbre that? Or is it also related to, at a bit more of a higher level, emotions that are being conveyed, right? Because if even from one note, an isolated sound that is being played by an instrument, you could even gather information about the emotional, the emotion that the performer is going through. So, and they're trying to convey that. So obviously the timbre changes slightly based on what they want to convey, because that what they feel transfers to how they're playing the instrument, how they're moving, and then that, of course, affects the timbre to some extent. So how do I define timbre? So keeping all this in mind, I thought, okay, so we have low levels and high levels. So let's just have these sort of higher levels, which are associated with identification, description, and categorization of prototypical mixtures of sources, aka polyphonic timbre. Ethnomusicologists, please forgive me. I'm going to say polyphonic. I'm sorry, but I can't think of a better word. Global sound is fine, but since we're talking about timbre, I'll just say polyphonic timbre. And so now you know the context when I say polyphonic timbre. Now, so the other question I am posing or I'm thinking about, and this happened this week, that actually when I was making this presentation, that okay, so we're talking about polyphonic timbre. Okay, we understand that in monophonic timbre, again, sorry, monophonic, I'm talking about single instrument sounds or single timbres, isolated timbres, that you have these levels of abstraction, but maybe in polyphonic timbre, it's no different. It's probably the same. That if I just take that and reorganize, it might be that the lower level descriptors of polyphonic timbre might be, you know, these metaphors that we use, that, oh, it sounds full, it sounds fuzzy, it sounds warm, and that's generally related to the acoustic properties. And then the higher levels would be, okay, it sounds like this person or this genre, or this is what they're trying to convey. So maybe there are two parallel levels of abstraction. I don't know, but this is something that I'm still thinking about. Okay, so most of my work has been revolving around polyphonic timbre. So the question is now, how do we deal with polyphonic timbre? Perceptually, acoustically, and in the brain, right? That was my starting point. And another thing is that when we're talking about forming these, abstractions of timbre, how long do we need before we actually form these abstractions? You know, in our head, how long do we take? Do we take a few milliseconds, a second, half a second? So the temporal span is also important because from previous studies, neuroimaging studies at least, we know already that spectrotemporal properties are very important in the process of either identifying or categorizing or discriminating timbres. So there's a temporal element as well. So that brings us to the next module of our talk, which is the temporal span, right? So how long, when do we start to accumulate all the information and form this idea of timbre, whatever that might be. Sorry, I have to be very vague because, you know, it's timbre after all, but okay. So typically, as I said before, timbre has been investigated as a static perceptual feature in neuroscience. But the brain is essentially, it's a predictive machine, right? There's always a temporal aspect to it. It's just not, it processes something now, and it does expect something else to arise right away, subconsciously, right? So our brains are essentially that, which means that the temporal element is very important to understanding how we perceive anything for that matter, any stimulus. And what we know, at least from some neuroimaging studies, is that, these perceptual processes operate on the principle of contrast or change. So in the sense that what we are actually what we more consciously perceive, and that is sometimes measurable, is the change. Not necessarily what, for example, we're right here. I know that there's a light, you know, these lights here, which are, I can barely see you all. But the thing is that I got accustomed to it. I'm not focusing on that, and it kind of becomes background. So I'm not focusing on, I'm just focusing on my, talk, which is changing. So in that sense, how are we processing sound or timbre? Is it always the changes in it, or is it the timbre itself? And I don't think we can always process everything all the time as it is, right? The brain is efficient. Why would it need to? It predicts and like, okay, I'm just going to code the change. I'm not going to code. Every time I look at you, I'm not going to say, oh, this is a chair, these are the people. No, I see that. You're constant here. So I'm just going to, if someone walks up, then I know that, okay, that's what I'm going to process. So the temporal span is important. And we also find, first of all, music listening is, after all, a continuous process, right? So timbre, of course, I can say this is a hip-hop song or hip-hop number, but then something changes within. But then it takes, it's just that there's some sort of a global distribution of those features which gives us the idea of the hip-hop timbre, for instance. So, but then when we want to talk about how the brain is processing things, we need a temporal context as well. Of course, depends on the question we're asking, but that's also important, even if it means that we're looking at it in the span of milliseconds. And another thing we noticed is that when we did some perceptual experiments, on polyphonic timbre, and we were extracting some features and trying to correlate with these perceptual, dimensions, what we found is that if I'm going to change the way I extract the features based on the temporal span, that the correlation value is going to change. So which means that there is no right way of saying this is the feature that I'm going to extract from this sound. Like some of you would already know, we have the spectral centroid, we have that which correlates with perceptual brightness. But how have you extracted that? You know, did I integrate information within a span of milliseconds or a second? So that it really determines what the acoustic correlate of a perceptual construct is, and then how that's encoded in the brain. So temporal span is indeed important. So just to give you some more background on what this polyphonic timbre is about. So this we conducted this study first to ask people like, okay, we're talking about music, we're talking about a small snippet of music, so how would you describe it, right? The way it sounds. So we gave them, they gave free responses, we gave all these scales where they had to pick, okay, can I describe it as dark, bright, full, rich, empty, simple, complex. So we did all that, and finally, after all the analysis, we realized that there were three main dimensions, perceptual dimensions of polyphonic timbre. And that would be fullness, activity, and brightness. So what do I mean by that? I will play you a few sound examples so that in the context of music, what those might indicate. So I'm going to start with low fullness. And high. So I don't know if anyone heard some, like, can I have a show of hands? Did anyone agree with that? Yeah, not bad. Well, you don't have a choice. It got published, so. Anyway. Okay, so then we have activity, right? So it's more related to the energy content. Low brightness. Okay, somewhat. It's not so far away, maybe, from these definitions. So what we found interesting was that it was spectrotemporal changes, which best these features, acoustic features, best correlated with these perceptual attributes. And interestingly enough, what we find is that fullness is related to the lower end of the spectrum, how much fluctuation happens there, because you would have heard the fuller sound was like lots was happening with the lower sounds and lower notes, and activity is more related to this fluctuations in the middle regions of the spectrum, and brightness was not necessarily related to the fluctuations, but rather it's more about the presence of high energy content, which is also similar to what we would find in monophonic timbre research. So at least we realized that, okay, so temporal span, that, you have to consider that to some extent. It's something important, like we are assimilating all the acoustic properties and forming these ideas. Now, and like I said before, the correlation strength between these acoustic features and the perceptual attributes, it depends on the temporal span of extracting the features. So I'm not going to dwell much on this temporal span. It's getting a bit more, boring technical. It's not that fun. But then let's move on to the dynamic aspect. So, okay, so we have some, rudimentary descriptions of timbre in music. So let's see, that is going to vary within any piece, right? Because music, of course, unless it's, I don't know, maybe a techno piece, it's fairly constant, I suppose. Or in these nightclubs, whatever they play. But then, because of all the signal processing and all the wonderful toolboxes that we have that allow us to sort of capture dynamic variations of these percepts, right? So I'll just give you an example. So this is brightness, but what you would see on top is brightness. Well, it's actually the spectral centroid. So just what you would see is a bar which would be moving based on how perceptually bright also it might sound. So below you would see the spectrum. So these are both acoustic features that we derive, and you can just agree or disagree with me whether they're representing perceptual brightness. So one thing you can see is that, yeah, it doesn't always coincide with our notions of brightness, and that's fine. But for a vast majority, okay. So for a vast majority, if it does somehow coincide, these features coincide with our perceptual concepts of that particular construct, then we can now look into the brain and see what's going to happen with those. But first, in order to do that, I have to put, as simple as that, I just have to put a person in the scanner and they just have to listen to music. I'm going to extract the features, make sure that they make sense perceptually, and we'll see what's happening in the brain, right? So that leads us to paradigm, right? From controlled to naturalistic. Okay. So, before I talk about that, I just want to give you an analogy in the visual domain. So what do you think the person is, feeling, or anyone? I mean, I like interactive keynotes, please. Not that I've given so many, sir. Joy, okay. Anything else? Excitement, joy, all right, great. But then if I ask you this question, how scared is this person? I mean, I could say 1, maybe. Okay, we should say so. If you say so. But actually, when you put it in context, right, it's a totally different thing. So, that's why when I decided, okay, we have to look at timbre, then, but I want to look at timbre in music. And that's why I wanted the context. And when I saw that most of the neuroscience research, at least on music, it was all done in what was called the control paradigm, right? So what does that mean? So the way it was being done is still being done, and for legitimate reasons, of course. I'm not dismissing anything because they serve as good. It's like a good support system to develop on. So typically they start with the feature of interest, pitch, timbre, rhythm. Anything. Just take that and carefully synthesize things which are quite controlled, so you know how to quantify that control. And then you subject the participant to that stimulus, and then try to model the responses, right? So that's how it goes, and it's quite controlled, and sort of, okay, this is what I'm doing, so I'll look for an easy to interpret as well. So I'll just play you one. It's not related to timbre, but it's related to beat processing. So I'm just going to play one of the stimuli that was presented in that study. And they played sort of regular and irregular rhythms like that. And then if you say that beat is processed, the clear beat is processed in certain parts of the brain, then I wanted to question that. Like how? Why? I mean, I can understand like something which is regular and irregular, but does that translate to how the brain processes things when music, when we're listening to music? And around that time, I think in 2004, studies in vision started to surface, where they started putting people in the scanner and they're watching movies, a long time. So it's more sort of naturalistic viewing conditions rather than just showing them faces versus apples and then saying this is the face area, So I don't think there's anything wrong with that, but I like context. Okay. So the naturalistic paradigm is where, that was the first study that we did, that we started with the stimulus itself. So let's take some music which has varying timbral content, right? And then we put people in the scanner, they're listening to it, we have the responses, then we extract timbral features, whatever they might be, because, how do I define what are those timbral features in music? I have something which I did before, okay, there's fullness, activity, brightness, yes, let's see what happens in a dynamic context. So once you have these features, then you want to model, somehow you want to find associations. So I'm just going to explain this one study to you because we did several studies after that trying to validate that and, replicate those results. So this was a study where we played Adios No Niño by Astor Piazzolla, and it's a long, beautiful piece of music. You never get bored of it. 8 minutes long. I'm not playing 8 minutes of music, but just so you know which one that is. Okay, so that piece of music, and we had musicians who were scanned. It was not intentional, I think, to choose musicians, because this was a pilot. Nothing was intentional, it happened. And so we had people who were scanned by listening to this piece of music. We extracted the acoustic features. And what's important is when we extract acoustic features, if you want to interpret the results in the brain, okay, I have my features, they're processed here in the brain, but what are these features actually representing? That's always important. And that's when we had to do some sort of a perceptual validation of these features, because it's just a bunch of numbers we extract. What does that mean to us? Because then we can say, okay, if this is more related to brightness of the sound, okay, and these are the areas where it's being processed, okay, so then I can make some, conclusions from that. So we did a perceptual test, and then we modeled them. So just to show you, because there are many times I get this question like, yeah, rhythm co-varies with timbre. I mean, there's so many co-varying things. What do you do with those? How can you say this is just timbre, or this is just tonality, this is just... Of course, that is a problem, It's not a problem with music. It's the best part of music. But computationally, it can be a problem, right? But then the kind of approach we took was, please don't get confused by all those terms. So what you're looking at here, so these are your timbral features, right? And the ones below are rhythm and tonality related. And what I want you to notice here is that this figure tells you how these co-vary. So if it's very bright, then you know that those features are co-varying. So for example, let's look at the third column, and you would see that flatness co-varies with spectral spread, right? They're kind of bright. So even if you don't understand, it's okay. It's just to say that we were clearly able to separate out, not separate out, but somehow find timbral features and the tonal and rhythm-related features quite well. So we were able to say, okay, if you see all the white blocks there, so all these rhythm and tonality features easily were separated. So that way we gave them labels, and then finally with the perceptual validation test, where we actually play snippets of the music and ask people to rate, okay, does this make sense? Is it how full does it sound? How bright does it sound? So that we actually have some sort of a continuous representation of a perceptual attribute of timbre. And we have the acoustic features as well. So now we had 4 timbral components, which is fullness, brightness, activity, as I'd explained, and timbral complexity. In hindsight, I think that's a very silly name, because timbre is complex, and timbral complexity doesn't make any sense. But the only thing we were trying to, the way we explained it was the presence of multiple timbres present, which don't cause much of a blend also, but it's just, a lot of many timbres just all over the place. So it's just a very complex timbre versus a very homogeneous, either isolated or more blended timbre. Okay. So the results, we were quite happy that they were in line with previous findings using control settings. So we know that, as I explained, we have the primary and secondary auditory areas, right? So that's something which are very important. So we find that. But we did find additional brain areas. And these activations are related to the cognitive areas in the cerebellum. Cerebellum is something that we don't think of when we think about timbre, right? We just don't. But then in the cerebellum, think about it as a small, it's like a small brain. It has its own sort of cognitive regions, emotional regions, which interact with, of course, the cerebrum, and then they have their own functions. But we found that, there's something going on in the cerebellum as well. And then we have these mirror neurons. They were all musicians. I think almost all of them knew how to play the piano. And there was this initial section, which is like 2.5 minutes long in the beginning, where it's just the piano. Just the piano. It's just like an intro for the piece. So we kind of figured that, okay, we know that when musicians are listening to a timbre that they're familiar with or that they play, it's related to some sort of perception-action coupling, right? In the sense that when I listen to my own instrument, then it's automatically somehow related to the areas of the brain which are needed to produce that. Because that's my sound and action is already coupled in my brain just because of practice and training. So that's how we interpreted that. But then we also found deactivations, or rather lower than average activations in certain parts of the brain. Now that's something that you cannot get from control settings typically. You just know there's been a change, but it's not easy to understand, was it a suppression or was it an increase in activity in the regions. So without going into what these regions are, I'm just going to go ahead saying that, okay, so what do? We do one study. We have polyphonic timbre, that's new in itself. We have a new paradigm, that's new in itself. So why should we sit and make all these big claims that, okay, timbre is processed in these regions? Of course, I define timbre in those percepts of fullness, activity, brightness, and timbral complexity. What is the reliability? This is a fundamental flaw in neuroscience, that people do not work on replicating their results, because first of all, it's not as interesting and it costs money, right? And people just don't do it, but it is extremely important, I think. And this illustrates that very point. This was something that was published. They put this dead Atlantic salmon in the MRI machine, and they subjected it to some visual things. It was dead, but they did find that red dot. Well, you can't see that from there, but they found one spot of activation, right? So this is something that to keep in mind, that when we find something in one study, it's always good, if we can, if it's feasible, to try and either do it on another a pool of participants, or just test it on them again. So if it's feasible. So this is something to keep in mind when interpreting results of any neuroscience-based study. So what we did was, so we decided to redo the experiment, and that was to assess the reliability of the findings, and also to validate the paradigm, right? Just it can't be just beginner's luck and that's it. So what we did was to replicate that study with the identical procedure, but just with a new pool of musicians, which were matched. And then what was the good thing was that the timbral features were most replicable, but not the rhythm and tonal, right? So we kind of figured that, maybe timbre processing is more a lower level sensory processing thing versus a higher level cognitive, element. So that's something that we said then, and yeah, that's probably true now that I think about it, that of course it causes all these abstract ideas of mood, emotion, and so many, it evokes so many things, but the processing itself might be actually more basic than we think it is. We don't know, but that's an idea. Okay, so then what about musicianship? We talk about timbre so much, but don't we think that maybe there's a difference in how musicians process timbre, how it's encoded in the brain? Would there be any differences? So we redid that, never with the intention of working only on timbre, but so I focused on this bit where, so we had musicians and non-musicians scan, and we had 3 pieces of music, 3 different pieces, so we are spanning genres, and we had Piazzolla, of course, and we had Stravinsky, right? So we had to find almost equal length pieces. And then this work is still in progress, by the way, but I just want to show quick results. There are differences for sure in the way the timbre is being processed. And but first, I'm going to show the result of if I combine all these people. Like previous studies had 11 participants, and that's common in fMRI, unfortunately. This time we had 36, not that that's any better. But what we do find, so the red shows the positive correlations, or the activations, and the green shows some sort of deactivations. So this was quite reassuring to us, like, yeah, our results were not too far away. So we are able to replicate the results again and again, not identical, but quite similar, and we can make some conclusions now. But then I don't have the animations to show you the results of the differences, but what we do find that in non-musicians, that you have larger regions, very similar processing timbre. I would have thought musicians, they have, I'm sure timbre would explode in their heads, and, there's all this going on. But the thing is that when you put all the musicians together and try to get the common areas where they process timbre, it's quite varied. Each musician, the way they react to sounds and timbres is different. So if you take a non-musician, they have more similarities in the way they process timbre. So that's something to keep in mind, at least even perceptually, that would be quite interesting to see. Can the non-musicians find the differences that, in small differences in timbres, or, maybe they're more homogeneous in the way perceived timbre, but then musicians, they kind of deviate from that. Okay, so now we have this paradigm. We have been working on it for, almost close to a decade now. But then we take it a step further. Like, so we know something, right? That, the auditory cortex are important and some other regions. So how well can we predict these? Can we predict timbre feature processing if I just give a new music stimulus, right? We have all these techniques. So let's just predict. Let's see that, can we predict activations related to timbre? And then the question was, how accurately can they be decoded from fMRI data? Now, this brings us to the next part of the talk, and also which brain areas, which is related to modeling, encoding to decoding. Okay, So just to clarify what encoding and decoding means, so encoding is related to forward inference, where I go from stimulus features, I take those and I try to predict brain activations, right? That's what I have sort of been doing so far, or explaining so far. And decoding, on the other hand, is the reverse inference, where from the brain activations, I want to predict the stimulus features, right? And decoding is extremely, it's in fashion, it's trendy to do decoding, so people are doing that a lot nowadays. And I'm getting all excited now. I think I want to move to decoding. We did one study, but I'll explain what that is. It's fascinating. Okay, so this decoding can be thought of as brain reading, right? So you want to, just by looking at the signals, you want to say, okay, they were listening to this piece of music, or this is what they were actually encoding. So this is the result. So let's deal with encoding to begin with. So this is an animation which shows you, okay, I extract my features and I'm going to predict the brain activations. So what you will see here, red refers to greater activation than average, and blue refers to lesser activation than average. So features have been extracted and we can predict. So I want you to pay attention to the ends, which is related to the auditory areas, which is very relevant to us for timbre. Okay, so you see some variation, and it's quite interesting that we see that, okay, the sort of the brighter it perceptually sounds, the greater the activation in the anterior part, certain parts of the brain. So it's kind of interesting that you can, with this technique, do this real-time simulation of that and test how well your model is. So we did. So the questions we asked were, how well can we predict timbral feature processing across different musical stimuli, and how can we have a general model just to say, okay, give me any piece of music, I'm going to do all this computation and I can predict, right, where timbre is processed in the brain. So there was this other study that we did, which was, so we had two sets of stimuli, right? One related to the Beatles. So it was side B of Abbey Road. You never give me your money. You only give me your okay, and then we had a medley of different genres of music. So we had like a wide range of music. And then it was the same setup where you scan them, you have the features, you try to model them and predict, whether we can predict where timbre is processed in the brain. But what we found is that the auditory areas, especially the anterior regions, which all the previous studies have shown that it is quite key in processing timbre, so that we could predict very well. Some of the motor regions as well, because we also had some rhythm-related features. And I will not go into the default mode network, but what we do find is that when we just cross-validate with all these data sets, we can say for certain that in the right auditory cortex, we can predict extremely well the responses to music. And we also know that there's some sort of a right hemispheric lateralization for timbre processing. So that way it kind of, gives us more confidence that, okay, so we can use this method, we can use these sort of features and say that, okay, this is where for sure that this plays a key role in processing of timbre. Now let's just quickly go on, I'm going to rush through now in the next 5 minutes. So we have decoding timbral features. So, okay, encoding is one way, but decoding also helps us sort of validate what we have found also, that are these regions actually contributing to the prediction of timbre, right? So how well they can be predicted in which areas. And it was the same setup for the Abbey Road. We thought from the brain activations, I'm going to predict the stimulus, the timbral features. And what we do find is that primary and secondary auditory areas contributed to decoding of timbral features. So I'm just repeating myself actually, but that's a good thing. If you find replicability in neuroscience, that's a very, very good thing. And we find that the higher proportions are in the right hemisphere. Again, that's also a good thing. And timbral features were best decoded compared to rhythm and tonality, which again means that maybe timbral processing is probably not, maybe it's not that much of a higher cognitive percept, but it's more basic and sensory. So just to show you how well it performed. So the one on top is a timbral feature. So these were the actual features from the music that you extract. But if I take my brain responses and see how well they predict, yeah, I mean, it's not that bad. And it's quite interesting that it certainly can decode aspects of timbre, but of course we can't reconstruct music, but that's a whole different question. So some recent studies have emerged where people are trying to decode genre, because that also somehow relates to polyphonic timbre, right? I mean, it's decoding genre is another way of looking at what timbre is actually representing in music. And here they use ways of combining several regions and trying to predict. So another good thing happening nowadays, people are moving from 3 Tesla to 7 Tesla scanners, so it's high resolution that gives you, better spatial resolution as well, so you kind of can see a bit more clearly what's happening in the brain. So what they did find using a 3 Tesla scanner, at least for this particular study, is that they just looked at the secondary areas, a very small region, and they did find that those regions, it had the highest correlation between similarity structure of timbral features of the stimuli, and it resembled how the STS or the secondary regions were processing, so better than tonality and pitch, which means that if you're talking about genre, it's timbral features that are best capturing the essence of genre, and they are indeed encoded in these secondary regions, right? And so they concluded that distributed population code in bilateral STS is responsible for genre discrimination. Now, once you go into high-end studies, they did find that, again, please just focus on the red areas, which are again the secondary regions, that better predicted perceptual genre classification than the primary auditory regions, right? So again, it's just repeating the same thing. It's the secondary auditory areas which seem to be encoding timbral properties. Okay, so that's pretty much what I wanted to say, but what do we do now? Where do we go with? So just a few points, what one can do maybe in the future. So related to the levels of abstraction, maybe the question should not be what timbre is, but what timbre can be. It seems to be taking so many forms. Timbre can mean genre somehow. Timbre can talk about the sound categorization for, like it's which instrument or how it's produced. So it can be so many things. So maybe it's good to ask the right question, not right, but ask the question and find the brain responses or interpret the brain responses accordingly. So you have to be very careful in framing the question rather than saying timbre is maybe this or that. Just make it, I would say, keep it simple. So easy to say that, no? With timbre, keep it simple. Okay. All right. So just to sum that part up, the secondary auditory areas seem to be crucial in timbre processing, and high resolution scanning is actually imperative now, because we already know that in the primary auditory pathway, in the midbrain, like from the cochlea, it goes to the brainstem and then goes to the auditory areas. There's already some sort of frequency decomposition happening. So maybe there's some representations of timbre already there. We don't know yet. But 7 Tesla scanning helps you do that, at least look more into the deeper parts. And then this very interesting thing for me is, but I don't know how to deal with it. It was a very recent idea. Deep learning, neural networks are making a comeback now. So they just, everyone, they use it to describe anything, everything, and, it learns everything. It's fascinating, but we can't interpret it. But, there's a particular case of those which are called autoencoders. So basically what you're training a neural network to, you give it the input and it creates several layers of abstraction and then produces the output. So if you use something of that nature, it could function as, in a way, automatic generation of latent timbre spaces. And that would be so fascinating. I still don't know how to go about that completely, but actually that certainly is one idea to look into. The temporal span, as I said, modeling change in brain responses, then the response itself might be an interesting thought, because we're always looking at, not the difference in how the brain's processing, but just exactly where and how it's processing and when. And then you have extracting, varying time windows for acoustic features important as well. And then you can have new features for timbre. Why did we come up with this list of features that this is it? Why don't we generate new features, which are different combinations of, spectral and temporal, which were extracted different spectral and temporal windows and nonlinear combinations. This might sound so horribly boring to you. I'm sorry, but yeah, just to say that with all the new technologies and all these coming up, we can try and push it further. And yeah, so another thing, of course, it's good to use more ecological stimuli. it's not 100% natural to lie in the scanner and listen to music, but, but it's good to just move a bit more and provide a certain kind of context also, right? And like I said, maybe before asking any question about the brain, you just want to clarify that, okay, this is what I'm investigating. Okay, I'm defining timbre in this way, and this is what I think it is at the moment, and this is what I'm going to investigate. So that, to keep that clear is very important. Of course, I cannot, I have to keep repeating myself. Replicability, reliability is important, and modeling, one important thing that we always think of, this timbre is a multidimensional, feature, right? So why do we keep looking at, we have to look at the way the brain processes from a sort of a segregated way to an integrative way, right? So people look at, okay, this region or that region is responsible, but no, it's a network of regions which would be responsible for processing anything. The brain, those regions don't work in isolation, so connectivity, as we call it, so sort of an integrated approach to brain functioning is something, that one must, there's an increase in studies that way. So you go from univariate to multivariate because timbre is multidimensional. Okay, and then of course, kind of method you use, your results would vary. Something, for people who want to venture into neuroscience, if you want to after this talk, I guess not, based on the question you ask and the method you use, you have to explain the results keeping all that in mind. You need to know your limitations as well. And finally, what I would look for is converging evidence by using multiple methods and multiple tests. And that's the only way that I can be sure that, okay, this is what, if I define timbre like this is where it might be processed, and that's it. I rest my case. So thank you for your kind attention. And yeah, thank you. Yeah.